what happens when you've got damping? Well, basically, here's our equation of motion, or differential equation of motion. Now I've got a Cx dot term. Okay. Our complementary function now has this decaying exponential in here, and obviously this is now omega d. That we've seen before. That's from last week. Okay, so we don't need to worry too much about the complementary function, but the particular integral. In this case, I'm assuming a constant rectangular forcing function. So xpi is gamma, x dot pi and x double dot pi is 0. So obviously that's quite nice. We can plug that into our equation. We get m times by 0 plus c times by 0, and we get k times by gamma. Xpi, gamma, is f naught upon k, as we had before. And so our general solution is our complementary function plus our xpi. Okay, that's quite nice and straightforward. And so we apply our initial conditions. Okay, so when you've got displacement being 0, cosine of 0 is 1, sine of 0 is 0, and then we have a1 plus f naught upon k equals 0. So it's quite clear that a1 is minus f naught upon k, as before. But this time, a2 we need the velocity. Okay, so we have to take the derivative of this equation. And as we saw in the tutorial 2 weeks ago, the derivative is a little bit complicated, okay, because you've got this, obviously, a function of two functions of time. Okay, so you have to use the product rule and the chain rule. Okay, so that's what I've done here. We end up with quite a complicated equation, but basically we have x dot pi as an exponential, as before, and then we've got cosine omega t times by this bit, and sine omega t times by that bit. Okay. If you go through the maths, that's what you end up with. And so setting t equal to 0, and we can work out what a2 is, and we end up getting zeta omega naught divided by omega d times by f naught upon k. So if you remember back before, when we had the damped case, a2 came out to be 0. In the undamped case, a2 is not 0. So if you insert those into your general solution, you end up with this. And then simplified out, you can see quite clearly there's an f naught upon k in each of these terms, so that can jump out. And we end up with 1 minus zeta, the exponential times by cosine, and then exponential times by sine. Okay, so that's in there, obviously, and then we have the 1 minus, which is that last term over there. So it's quite clear to see that what we've got is we've got this bit here is a constant forcing function, okay, minus a decaying sinusoid, which makes sense, doesn't it? If you apply a constant force, the thing's going to start oscillating, and then it's going to settle down to that constant force. Okay, there's the static deflection. Okay, and this is obviously is a sinusoid, okay, that decays. And so if we plot that, you end up with this sort of response. Here's the undamped case. So you apply the constant force, and it oscillates up and down between 0 and 2 f naught upon k forever. Obviously, in the damped case, you applied some damping, won't overshoot as much as this, and obviously the oscillation will settle down until you hit static deflection. So as time approaches infinity, you end up with f naught upon k as your response, which makes sense. If you think about damped systems and stuff, okay, you apply a constant force, you get this sort of response. Okay, think about I guess a car that you've lifted off the ground, so the wheels are not on the ground. You then put the car on the ground, okay, and the car will oscillate and then damp out. And hopefully, if your dampers are working, you won't get much overshoot, and it will damp out very quickly. Okay, if your dampers aren't working very well, obviously you end up with a bit more of a oscillation. But it's a real system, and so you will actually damp out in the end. So that's the constant force being applied.